Hello everybody, my name is Ruhan and I'm back with another video on my YouTube channel. As you probably would have guessed from the video title, today we'll be going over why 45 degrees or pi over 4 radians is the best launch angle for any projectile object and how that maximizes the total distance traveled by that object. However, something very different to other YouTube videos on this topic, this proof is actually going to be geometric. So without further ado, let's get into the video. So first of all, we need to understand how the scenario is modeled. So before we get into anything too specific, we need to understand what projectile motion is. So in this case, we're going to have three main things. We're going to throw an object with a velocity v at an angle theta into the air. Now that object, if you assume that total energy is conserved and that air resistance is negligible, will travel in a parabolic manner. Now, this is something you probably would have learned in your two-dimensional motion class. I wouldn't be going into too much detail. And when talking about this motion, there are three main stages throughout this process. There is stage A, where you have your initial launch velocity and angle. Stage B, where the magnitude of the velocity stays the same, but the direction changes. The last portion is component C, where you have basically the same sort of direction, however, the angle is measured from a normal. So basically, you're sort of rotating it this way. Or you can think about it like this. So if this is your initial, so this is just going to be a reflected portion of your velocity component. And because total energy is conserved and air resistance is negligible, the size of this V, the size of this V, and the size of this V will all be equal. Now let's get into what V really means. So for convenience reasons, we can't really consider the vector V as a standalone. We therefore have to divide it into two components. We talk about V sine of theta and V cosine of theta. So basically what that does is it takes this vector and it breaks it apart into two components, both of which are also vectors. The V sine theta, as you can see, is the vertical component of this vector, and V cosine theta is the horizontal component of this vector. Now, since this whole video is about proving why 45 degrees is the best angle to maximize distance, we need to really have an expression for what distance is. And I'm pretty sure a lot of you would agree that distance would be the horizontal component of this velocity. Basically, if you take this velocity and you break it down into just the portion which is covering this distance times the time it has to cover that distance. This just comes from the distance is equal to velocity into time. However, since V in this case must be the horizontal component, it's V cosine of theta, where this is theta and this is V. Moving on to the next part of the video, we need to understand the needs. So in this expression, we have two components. We have V cosine theta, which is V, and times t. So this is just our normal velocity, and this is our normal time. Now, V and theta are two components which are already given, as you can see here, and it's a question about calculating time. Now, if you look at this parabolic motion and you assume that we just launch an object straight ahead, because it does not have any height, it will just stop on its tracks. It will not move forward because it will just collide with the ground and lose all energy. Now, that is why when we calculate time, we have to consider how long will it have time to spend in the air, and that is the time which we're basically going to use, and it's the air time which is necessary to us. And in order to calculate the air time, we need to now consider the vertical component of this parabolic motion, and therefore we need to consider V sine of theta, which is your vertical component. Now, the only reason why I'm only looking at one half of the parabola is because parabolas, if you have studied functions, right, like you have your normal parabola, these are normally symmetrical by their reflection point, which is basically calculated using negative b over 2a. In this case, this is equal to 0 because we're modeling our parabola in that way. Now, because they are reflectively symmetrical, they're symmetrical around that y-axis, the total distance is just 2 times d, and it's proportional. So we don't really need to get into the complexities of that. We just need to consider this 1/2 of the parabola. Now let's move on to trying to calculate time. Now, in order to make these calculations easier, I have given you 2 graphs. The first graph is the actual trajectory of our projectile, which is launched at angle theta. Now, this is point A, this is point B, and this is basically constant throughout. This is point A, this is point B, or if you want to look at the full scheme of things, this is point A, this is point B, and this is D, and this is H, right? So this is basically modeled here. This is H, this is D. Now, what I've done to make everything much more simpler is I've modeled the vertical component of the velocity, which is basically v sine of theta. Now, I have modeled it in a velocity to time graph. As you can see, at point A, you have maximum velocity. That's where you launch. You have maximum vertical velocity. Now, there is a negative acceleration acting on that velocity in the form of the gravitational force. Now, in this case, the acceleration must equal negative g because we're considering up to be positive. Therefore, if the force is acting down, it must be negative, and g is approximately equal to 9.8 meters per second squared, which is the natural acceleration due to gravity on Earth. Now, in this case, we can see the gradient of this curve would be negative g. Point A is maximum, point B is 0 as the vertical velocity goes. Now, we have an expression for acceleration here. This is your normal formula for acceleration. We have A is equal to delta V over delta T. Now, in this case, T does not need to be in the delta because we're starting from 0. Now, moving on to the actual calculations, we can see that this expression, because we're solving for t, right? T is what we want. So we want t to be isolated in one side. So we can write it as a into t is equal to velocity final minus velocity initial. Now, if you look at the graph carefully, we're actually given the initial velocity. Like, the initial velocity would be the velocity at the start of this system, which must be a, and as we know, this velocity is the launching velocity, the vertical component, which is v sine of theta. So we can basically substitute that in, and we also know that a must equal negative g, so we can also substitute that in. So at the end, we'll have a formula which would look like negative g into t is equal to velocity final, which, as we know, again, must be 0 as the final velocity in this case, because after this it's going to start going down, so this point must be 0. Therefore, velocity final is 0, and you have minus the initial velocity, which is v sine of theta. So now we can start isolating things, and because our final goal is to get t, let's actually substitute negative g over to the other side of the equation. We'll do that just by doing this. T is then equal to negative, remember the negative sign, v sine of theta divided by negative g. Now we can do some mathematical magic and cancel out these negative signs. So we're left with this expression in the end. Now that we have an expression for t, we have an expression for d, we can actually start substituting everything through. We know that d is equal to v cosine of theta into time, which can then be substituted as d equal to v. D is equal to v cosine of theta into v sine of theta divided by g. Now what I'm going to do is I'm going to take this, this, and this. So these are basically constants. So I'm going to put them together. I'm going to leave these, which can actually vary with theta alone, because again, we're looking at theta. We're trying to prove everything in terms of theta. We're trying to get that angle. So it's beneficial to have those isolated. So we can have v squared divided by g. That's our constant. And then we have thing which we want to isolate. We have cosine theta into sine theta. Now this is where our actual proof comes in, because now we have an expression for which we can try to maximize d. So we want d to be the biggest it can actually be. And in order to do that, we need to ensure that this cosine theta and sine theta, their product, is always maximum. We know that we have this expression and we want to maximize this. Now we have to find a value of theta for which sine theta into cosine theta is maximum. Now what I've done here is, instead of looking at trig identities and trying to solve it down into a trig identity, what I've done is I've made a geometric representation for what sine theta into cosine theta actually is. So as you know, when you multiply two things, when you multiply two lengths especially, you take it from a one-dimensional system to a two-dimensional system. More specifically, you have a rectangle. Now, one very important thing to note here is, if this is sine theta and this is cosine theta, because we're talking rectangles, either sine theta must be greater than or equal to cosine theta, or cosine theta must be greater than or equal to sine theta, no matter how you look at it. One of these things has to be true. Only one, though, because both of them cannot be true at the same time due to logic. Let's say you have a value a, right? And you multiply it with the value b. However, let's say b is less than a at all times. Now, just out of pure curiosity, I want to ask you, now, in which of these cases would the area of this final square or rectangle be the greatest? And as we know, the largest rectangle by area is always a square. Now, using this same logic, because we know that the largest rectangle must always be a square, we can actually calculate a value for theta here using only our geometrical representation. So for this to be a square, we basically need cosine theta to equal sine theta. Now, if you guys know the unit circle even a little bit, which I assume you do if you're watching this video, you know that if we draw a unit circle here, this is only true for when you have a point here such that its coordinates are root 2 over 2 and root 2 over 2, and it must be the diagonal of a square, which is always degrees 45, or for the radian fans out there, the theta must equal to pi over 4 or 45 degrees. And that was my geometrical proof for why 45 degrees gives us the maximum distance in projectile motion. Of course, ignoring air resistance and assuming conservation of energy. Thank you very much. If you like this video, please subscribe. If you really like this, I'm also going to try to draw a thumb. Yep, please leave a like down below. And this has been Ruhan. I hope you like this new form of video on my channel. I'll try to keep updated more. Thank you very much. See ya.